The first definition of air in the Oxford English Dictionary is the invisible gaseous substance which envelops the earth and is breathed by all land animals. Next to water and food, it's one of our most precious commodities. The third definition is the atmosphere as a whole, or that which is in a person's immediate surroundings, the free or unconfined space above the surface of the earth or above one's head. The fifth definition for air is air regarded as necessary for well-being, the fresh air of outdoors, as distinct from the stale air of a confined space. This definition actually is not new. It's cited as being used first in 1393. It's now a known fact, as reported by the EPA, that indoor air is 3 to 5 times more polluted than outdoor air. We also know that Americans, at least, spend almost 90% of our time indoors, that air in confined spaces. And it turns out that a third of the air that we will breathe in our lifetime will be in one room, and that's the bedroom. The big question is, what is in your bedroom? What's creating that air? And what's the air that we breathe? For me, it was through an acronym, IAQ, that I first became aware of the effect of the places and things that we design for daily life and how they can have an effect on the physical and neurological health of humans and animals and organisms. IAQ, indoor air quality, or the air and the quality around buildings and structures, especially as it relates to the health and comfort of building occupants. That's a definition, again, from the EPA. Scientists and engineers and medical professionals have proven for many years that the things around us off-gas or emit chemicals from the materials they are made from, and that many of those materials which compose our indoor environments contain substances and chemicals that are harmful to human health. As a designer and of interiors and furniture, this understanding fundamentally changed the way I practice and the way I teach design. I realized that just as the knowledge of materials is essential for any design or architecture practice, so is an understanding of basic chemistry of materials. Because materials, as at a molecular level, have everything to do with human health. As designers of spaces and objects, we need to know about the context of the materials that we work with and their impact, because materials emit, break down over time, and shed finishes and their molecules into the indoor environment. And we breathe that air, often full of harmful chemicals, particulates, or microscopic dust. And we inhale that, and it becomes part of our biology. Exposure to polluted air is now proven to be linked to poor neurological functioning and cognitive deficit in children, as well as linked to asthma and many other diseases. We also know that air, this gaseous envelope around our planet, is threatened also by the material world through manufacturing processes. Carbon pollution of our atmosphere is one of the greatest threats to humankind. So protecting clean air is at the front of minds of everyone concerned with sustainability these days. Air above the surface and above our head is now a health concern. So for this panel, we're going to approach, I think, many different interpretations of what we mean by air, which is kind of exciting. I have the great pleasure to introduce the people who are working in a bunch of inspiring disciplines. Ooh, even looking at them makes me inspired. To what we're exposed to inside and out. And in each of your programs, you'll have a lengthier biography. So I'm just going to give a very brief description of each of them, and then they'll describe themselves. Laura Vandenberg is an educator and an environmental health scientist who trained as an endocrinologist. Dr. Vandenberg is an associate professor and graduate program director in the Department of Environmental Health Sciences at the University of Massachusetts Amherst School of Public Health and Health Sciences. Her lab focuses specifically on endocrine disrupting chemicals, Laura is also a faculty on our e-learning program, helping students from all kinds of disciplines really understand the basics of chemistry, which might be hard to understand, but she does an amazing job of converting the designers. So thank you for coming from Africa a couple of days ago, or yesterday or something. Thank you. Aaron Dorf, sitting next to Laura, is an architect devoted to sustainable thinking. He's director and senior architect at Snohetta, a Norwegian architecture firm with offices here in New York and around the world. Aaron looks after Snohetta's North American powerhouse work, a body of projects and partnerships that follow Norway's strictest sustainability practices for zero emissions buildings by promoting ultra-low energy use, zero or positive emissions, and healthy materials. Aaron also contributed to our e-learning course with his expertise, so thank you for that as well. And Ginger Craig Dossier is an architect turned scientist, material innovator, and also an educator. She's co-founder and CEO of the amazing company Biomason, a revolutionary organization utilizing biology for growing cement-based construction materials. Ginger has taken sustainable material development from prototype to commercial production, which is pretty incredible. And she's super knowledgeable about sand and bacteria. So thank you all for coming. I think we'll start with Laura, and then we'll move into Aaron, and then Ginger, and then we'll have a discussion afterwards. So please help me welcome them.
Good morning. It's so great to be here. Thank you for the invitation to speak. So I think you get to listen to me first. I'm going to talk to you sort of setting up this session focused on toxic substances, some relation to air, and also hopefully inspire you with some thoughts about what we can do to reduce exposures, because there really would be some benefit to this. So I'm going to start by mentioning that humans are exposed to chemicals, and I don't just mean chemicals like we're full of chemicals, my body is made of water, water's a chemical, but I'm worried much more about toxic chemicals, and we're exposed to them from all kinds of sources in the built environment and in products that we use in our everyday lives as consumers without ever really thinking about what's in those products. And it was about 10 years ago that one of the first studies looking at children at the moment that they're born, looking in the blood that's found in the umbilical cord and looking at amniotic fluid, that it was found that there are hundreds of chemicals that babies are swimming in the environment before they're born. Hundreds of chemicals. When I first read that study, I think I was a graduate student or a postdoc, and I was getting ready to give a talk, and I was talking about this to my husband, who's not a scientist. And he said to me, how many chemicals should be in the amniotic fluid before a baby's born? Now, if you think about that for a second, it's not actually a question for a scientist. That's a question about our values. That's a question about our society. How many chemicals should there be in amniotic fluid? How many things should we be exposing unborn children to against their consent? And usually, again, these are things that the mother isn't even aware that she's been exposed to, and she must have been exposed to them for them to get into the amniotic fluid. Now, I don't want to confuse this concern about chemicals with a newfound language like chemophobia, right? This is not a phobia. And if it were a phobia, there's nothing you can do to get away from these chemicals. Again, this is an issue of knowledge, consent, and a question about what are these chemicals actually doing if we're being exposed to them. Now, I'm trained as an endocrinologist, and my interest in this topic really is because some of these chemicals that we're exposed to on an everyday basis have hormonal activity. Some of them mimic the hormones that our bodies make naturally. Some of them block the ability of the hormones that our bodies make to do their job. And this is concerning because at every stage of our life, virtually every aspect of the function of our body, of our physiology, is coordinated by hormones, from conception until death. The bagel that you had for breakfast, its digestion is dependent on hormones. Your ability to keep your body warm sitting in this room is dependent on hormones. Your ability to maintain bone health so that you can stand upright, dependent on hormones. So it's not just the fun stuff that teenagers like to ask me about, because they do ask, but it's virtually everything, including the hormones that are responsible for brain development, for the development of your organs, for the choices that cells make during development about whether or not they'll become fat or bone. So our exposures to these chemicals occur in everyday lives, and they're typically low, which is why we don't notice them. It's not like I'm getting into my shower in the morning with a plastic shower curtain and dropping dead because of the plastics in that shower curtain, right? We're not talking about the kind of toxicity that we, of course, should be worried about when we're being exposed to things out in the world. We don't want things that cause us to just drop dead. Instead, we're talking about chemicals that are more insidious. We're exposed to them at low doses, so we don't really notice that they're there. And here's a bunch of different classes of chemicals that are off-gassing from products that we're using. They're leaching from the products that we're using. And we're not aware of them. And some of them, we even take some small satisfaction in them. The idea of buying a non-stick pan to be able to cook the perfect egg, right? Who doesn't want that? When you come home from work at the end of the day and you sit down on your sofa and it makes that lovely swoosh sound, right? That's what's releasing flame retardants from the foam of your sofa. And not only are we breathing in those chemicals, our children are eating them, because dust that's found in our house is comprised of hundreds of these chemicals that are released from products. So I often hear, we've all been exposed to these things and we're all fine, right? That comes along those lines of like, you're just creating hysteria, this is chemophobia, you're trying to cause people to be afraid of things. And what I would tell you is, we are not fine. As an endocrinologist, we've been studying the trends, the secular trends, in conditions and diseases that affect human populations. And we see increases in those diseases. Increases in asthma, ADHD, breast cancer, testicular cancer, decline in sperm count, increase in infertility rates, increase not just in type 2 diabetes, which we think of as a lifestyle factor disease, but type 1 diabetes. Increases in obesity, increases in learning disabilities. Do I need to go on? We are not fine. We are not okay. And the changes in the prevalence or the incidence of these diseases has occurred over very short periods of time. When my grandmother was young, the risk of breast cancer was 1 in every 22 women. Today, the risk is 1 in 8. The difference between my grandmother's generation and mine cannot be explained by genetics. There aren't that many genetic changes in a human population over 2 generations. So we must start going and looking more closely at what has happened in the human environment over those 2 generations. And my work, and the work of many of my colleagues, comes from controlled studies in laboratory animals. Now I tell you, no one enjoys killing mice and rats, but humans are generally non-compliant patients. And if I said to half of you, for the rest of your life, you're not allowed to touch anything plastic, not only could you not do that, but you would probably not be willing to try. Maybe some of you would be willing to try. It's hard to look at these relationships in humans. That doesn't mean we can't do it. And in fact, human studies are showing us that there are relationships between exposures to these toxic chemicals and adverse health outcomes, including the diseases that I listed just a few minutes ago. But in controlled animal studies where we can say half of you are going to be exposed and half of you aren't going to be exposed, we can show that these environmental chemicals that people are exposed to can cause these diseases. And we can show this even when animals are exposed to low doses. The chemical that I spent the first 10 to 15 years of my career focused on is BPA. When I speak to my own colleagues, they roll their eyes. We're tired of talking about this chemical. We all know it's bad. For some of you in the room, you've probably heard of this chemical, and you might not know, why are we talking about this? There's all these things that are now labeled BPA-free. That might be the extent of your knowledge or understanding about BPA, is that when you see something labeled BPA-free, it helps you know that BPA might be bad. BPA was originally investigated for pharmaceutical purposes as an estrogen. It was placed back up on the shelf when a better pharmaceutical estrogen could be used. And then what often happens is that chemicals that are discarded for one purpose become useful for other purposes. So while it was not used as a pharmaceutical in the 1930s, it got pulled back off of the chemical shelf in the 1950s because of its amazing properties to be used in plastics, in epoxy resins. And this is why we now find it in the linings of food and beverage cans, in a lot of consumer plastics, including in sports and medical equipment that are meant to protect us, keep us safe, or improve us in some way. And it's also used in thermal receipt paper, which means that every time you handle a receipt, it's being rubbed off of that receipt onto your hands. And if it's not BPA, it's probably something called bisphenol S. The effects of BPA on hormone-related outcomes are extremely well documented because just as pharmaceutically it was useful as an estrogen, it is an estrogen when it enters our body, even though it's entering our bodies from leaching from plastic products and leaching from epoxy resins and rubbing off of those thermal papers. And we know from animal studies, as well as fairly robust human studies, that exposures to low doses of BPA affect reproduction, male and female, affect development, health, and disease of the mammary gland, which would be the breast in women, affect metabolic endpoints, including obesity, diabetes, and liver disease in rodents and in humans, and affect brain and behavior, including some fairly robust studies that have been done in children where they measure what was in the mother's body when you were in gestation, and how do you behave, and how do you act as a child. Unfortunately, as I sort of hinted to with the thermal receipt story, BPA is just the tip of the iceberg. As we've started to phase BPA out of consumer products, and that's not because any regulatory agency has taken action, it's because consumers have said, wait a second here, I don't want an estrogen in a baby bottle. Instead, we're replacing it with other bisphenols. My lab has been studying bisphenol S, which is a major replacement for BPA. And it's in baby bottles, it's in consumer plastics, it's in food can linings, and it's in thermal paper, all of the same things. And when the first study was published that showed that BPS, like BPA, is an estrogen, a reporter called me and he said, Laura, I am not a chemist, but wouldn't you think something called bisphenol S would act like something called bisphenol A? And I said, Brian, I am not a chemist, but yes. When I'm asked to talk about endocrine-disrupting chemicals with the general public, I'm often asked, who is supposed to protect us from these chemicals? Like, isn't it someone's job to say, that's an endocrine disruptor. It affects hormones in babies. It will affect the development of babies because that's what hormones do. So let's not expose children or babies or pregnant women or the elderly or you to these chemicals. In the US, chemicals are regulated by the US EPA, which regulates pesticides, and it regulates industrial chemicals, which includes pretty much everything that goes into building materials. It regulates what's found in the air and what's found in the water as a pollutant. The FDA regulates cosmetics, personal care products, pharmaceuticals, and food packaging. Currently, we only have legal statutes related to endocrine disruptors for pesticides. And the statute requires that pesticides be evaluated only if they have estrogenic activity, so forget about all the other hormones. To date, the FDA has evaluated with any level of detail only 52 pesticides for endocrine disrupting properties. There are thousands. And I just want to make sure that we understand what the real cost is, because the EPA, for all of its strengths and weaknesses, in its regulatory statute, requires that it consider the economic cost of any regulation that's passed. This is why even a product as dangerous as asbestos took almost a full decade to regulate in the United States, because the asbestos industry could make the argument that it cost them something to be regulated. There is a cost to not regulate as well. And that is not usually evaluated by decision makers. It is not evaluated by regulators. Instead, it's starting to be evaluated by academics like my colleagues at NYU, which looked at just a handful of endocrine disrupting chemicals and just a handful of diseases. And they calculate costs to the American public annually of over $300 billion. So what do we do when regulations fail to protect public health? What can you do? I think the first thing we need to do is acknowledge a need for a paradigm shift. In a paradigm shift, the first thing that happens is that you deny that there's a problem. The second thing that you do is you say, okay, it's a problem, but it's extremely rare. Like endocrine disruptors, like maybe BPA is bad, but otherwise you're just making a big deal about other things. The third thing that you do is you suggest an inability to do anything about the problem. You say, okay, it might be a widespread problem, but it would cost us way too much to do something about this, so we can't. The third thing you do is accept that there's a problem. And we're not there yet, right? We just heard about how we have people who don't accept that there's a climate crisis right now. In the world that I work in, there's a large lack of acceptance that there's a problem, which means we can't get to the last step, which is the most important step, which is accept that there's a problem and enforce a change. The second thing we need to do is to learn to identify manufactured doubt. I could give you an hour-long lecture on this. It's one of my favorite things to talk about because it's the thing we don't talk about, the elephant in the room, which is that there are vested interests in preventing change. The tobacco industry wrote a literal playbook of how they could manufacture doubt about the harmful effects of their product. This happens over and over and over again. See asbestos industry as an example. Number 3, protect vulnerable populations. Yes, I worry about the fact that my house is full of toxic chemicals, but we should also worry about the fact that there are workers who are being exposed to massive amounts of these things as they're creating the products that we live in or that we work with. So my exposure, yes, I'm concerned about. Someone else is being exposed to whopping amounts that it takes to fabricate materials. We release these things and they affect wildlife, and wildlife are not equivalently vulnerable as we are, especially as they manage other environmental factors, like impinging on their habitats and climate change. There are vulnerable populations because they have illnesses, like people who have asthma or autoimmune diseases. There are people who are vulnerable because they happen to live a particular lifestyle, like being vegetarian and eat a lot more of certain kinds of foods, or being carnivores and eating a lot more of certain kinds of foods. And then there's the biological vulnerability, the vulnerability that comes with being very young or very old. And we need to fix the approaches that we use to test chemicals, including, in my world, what do we decide means that something is toxic? Does the animal have to die for us to acknowledge that a chemical is toxic? Or are other diseases important? In which case, we need to develop tests that match the diseases that affect humans. We need to make informed choices, which means that we can't be afraid to speak up about these things just because someone's going to use a word like chemophobia or chemophobe or hysteria to label us. I defy those labels. I'm allowed to talk to you about these things, even if it makes you a little bit afraid, so that we can do something about them. And I'm going to leave you with the thoughts of Rachel Carson, and if you haven't read Silent Spring, go read it. It's still an amazing book 50 some odd years later. She said, if we're going to live so intimately with these chemicals, eating and drinking them, taking them into the very marrow of our bones, we had better know something about their nature and their power. These chemicals are in the bodies of babies before they're born. We had better know something about what they're doing. Thanks.
Hello. I guess in these multi-speaker formats, there's always the risk that someone who speaks right before you kind of knocks you over and makes you forget all the stuff that you came to talk about. So it may have just happened. My name is Aaron Dorf. I'm a director and architect at Snøhetta. I have been working with Snøhetta for 12 years now. I've had the good fortune to work on a number of projects in the city, around the country, and I'll talk about one particular project in this discussion that really centers around how we think about healthy materials. The particular focus of our practice, we're international. We've been a practice for a little over 30 years now. We've been working around the world in, primarily North America and Europe, but of course, projects and offices we have been emerging around the world now. In the U.S., we have the New York office, of which I'm a part, and we have a San Francisco office, and together we kind of comprise the North American and South American work. However, we also have been focusing on a body of projects that tries to take these issues of sustainability, of healthy materials, so seriously that we want to explore the boundaries of how far you can push projects in practice, beyond the levels of certifications that we have today, that seeks out partners. Some of which you can see kind of at the top of the slide, who want to invest in a research relationship through the project and with us in order to figure out how to transcend some of the boundaries that we, even admirably create when we have systems like LEED and other things like that. Invariably, those things can become checklists, and those checklists can become something that makes you feel better about what you've done, but maybe you haven't totally addressed some of the issues. Some of the projects that we have become well known for over time are some of the kind of bigger projects around the world. San Francisco MoMA expansion, which I had the good fortune to work on, completed in 2016. The Oslo Opera House completed in 2007. And National September 11th Memorial Museum Pavilion, the little building that's on top of the memorial. That's actually the project that brought us to New York in the first place. These are all projects that we feel proud of, that give us a chance to have an outreach that's global. However, this other body of projects that we call our powerhouse projects, essentially what they are all different research initiatives into zero emission buildings. And while I won't specifically talk about all of the issues that come with zero emission buildings, the principle of them is really that you take your emissions reduction through whatever phases of the project you've intended to address, whether it's in the building phase, the operations phase, the construction phase, or the deconstruction phase. You try to reduce your carbon footprint to zero or positive, which essentially means that your energy production has overcompensated for all the energy that went into the products that you built with. So some of these are our projects that have been kind of pioneering those things in our practice and in the world. And so we began this effort in our Norwegian office first. It's probably not a big surprise that you can really start to be more progressive in an environment like that, where there is a more unified acceptance, I think, of these kind of practices. What's important to us is that we can find ways to adapt this thinking elsewhere in the world. So we were presented with a really interesting problem, a few years ago, and approached by Green Buildings and City Center at Harvard University. They're a part of the GSD, but they operate fairly independently as a kind of a think tank for green building practices. They had this little house in Cambridge, just behind the GSD. It's on Sumner Road, an old wood frame house from 1925. And they had been working in it for a few years. It had been adapted from a single-family home, lightly adapted prior to their use. And they wanted to know how to kind of create one of these zero-emission building projects that also has nested within it a certain amount of research that they had already begun on their end. So they brought us together, knowing that we had done some of this before, with their PhDs, with their entire team that works in this house, to show us a kind of a booklet that they had made, which was how to transform this house into a zero carbon house, a house that requires zero energy to run on, or nearly, and addresses the issues of indoor air quality, healthy materials, daylighting, all of these things. And so that was really the charge that they gave us. Here's what we've done. What would you do? And so we started with that problem, and then they gave us really these 4 requirements that we had to address. This was the program of the project. There were no spaces that were particularly critical. There were no other goals that they had in mind. This was what they told us that we had to achieve. And so these 4 zeros became the kind of guiding light of the project. So the intent was to get this house to be at or near zero in terms of the energy required to run the house for heating, cooling, and electrical needs, to have zero mechanical ventilation, so in other words, 100% natural ventilation, zero electric lighting needed, so the way that we explain that is 100% daylight autonomy, so to make sure that you can run the house with zero lights on as long as the day has some daylight and it's not too cloudy, and zero or positive carbon emissions. So I could talk about any one of those things in a lot of detail, and I will kind of focus on the air aspect of this, but I'll probably touch a little bit upon all of the other aspects as well. This was a diagram that the Center for Green Buildings and Cities have created kind of since the project. And it kind of talks about the differences between a standard building, a standard house, and what this house is trying to achieve. It doesn't have zero systems, but essentially has very few. It's not a totally passive house, but it requires a certain amount of energy to run on, but that energy is extremely minimized. And essentially what it does is it's constantly measuring itself. So the house is embedded with hundreds of sensors. It's embedded in the exterior materials, on the surface, inside the walls, at different heights. They monitor everything from air pressure to temperature to carbon dioxide to air velocity in the house at different points of the house where air moves in and out of it. And so this censoring and the weather station, et cetera, that essentially kind of helps run the house, these things really become the systems of the house. So you go from a place where you have lots of piping and lots of ducting and all of those kinds of systems, and this house really runs on wiring. And so this is kind of we have all these construction photos with these bundles of wires that are essentially required to not necessarily run the house, but this house is meant as a lab. So what they want to do is make sure that they can monitor the way that the house was designed and to see if it's performing to its aspirations. So as we looked at the issue, we were also looking at the context of how buildings respond to their environments. So in a similar environment as an average, a house in terms of the energy it uses in a square meter in this case, it's really the only way you can create apples to apples comparisons for things of different sizes and types. Its average house might use 232 kilowatt hours per meter squared per year. It's a rough average in this climate. A passive house, which is a really aggressive way to look at energy use reduction, it doesn't look at zero carbon, though. That's a different issue. And so a passive house has its own challenges with respect to that. But in terms of minimizing energy use, it does a really good job. A passive house can cut the typical energy use in half or better. What a passive house does do that works against what we're trying to do is a passive house has a lot of insulation. Insulation is a major factor in terms of carbon emissions. A passive house is more insular than we're interested in. It's not totally naturally ventilated. It depends on some ventilation systems and energy recovery systems that are driven by that. The goal of our project was essentially to cut that down even more to an aggressive goal of somewhere between 1/8 and 1/10 of the energy use per square meter of an average house. And so this was an early study, an early rendering that we did. It includes both the house, which you see in the background, and also an expansion in the rear yard. That's where this view is taken from. And so the phase one of the project, which I can talk about today, is the work we did on the house. As I said, the house is not without systems, but the systems are radically minimized, and they're balanced against a lot of other passive techniques in order to make this house run at those extremely low energies. The other thing that's worth mentioning is that one of the critical aspects of zero-emission building is to radically reduce energy use. That sounds obvious, but it's different than, let's say, North American zero energy building, which doesn't incentivize lowering energy use. What it does is it incentivizes replacing your energy use with other sustainable practices like renewable energies that you can put on site, you can put off site, you can pay energy providers to give you offsets. In a Norwegian zero-emission building project, you can't do that. You actually have to work within your footprint that naturally limits and incentivizes you to keep your energy use extremely low. And so some of the systems that we have, so natural ventilation systems, they run through the windows, obviously, but there's also a solar vent that drives natural buoyancy. The windows and the skylights, each of them have an automated and a manual portion. So the automated portion runs off of a Danish motor that sits inside the window. And that ties back to a CPU in the house that essentially runs all of the systems together. So the windows are constantly opening and closing, even in the winter when they have to do air replacement at night. There's the other systems that are in the kind of phase one of the project and improved envelopes. I'll talk a little bit about that in a minute. But we had to get our air tightness, but also our insulation up to a certain level to achieve these goals. But we couldn't take our insulation too far in order to make sure we got a zero carbon balance. And we also had to be careful about the materials we used. Power production on the roof is critical for offsetting energy. So that's something that we studied many versions of it from customized products on the roof to standardized ones. Thermal energy storage, this was a big deal. We had to add a lot of mass to the house in order to make sure that we could actually, that the thermal inertia of the house was slowed down to the point where you could respond during the seasons, and the house could act primarily passively during most of the year, except for the extremes of the winter, like deep winter and deep summer. And then almost zero energy use. So we do use some geothermal wells that basically provide ground thermal coupling. They're not. We have a heat pump that runs the water that comes from 400 feet below the ground, but it's not artificially heated or cooled in any other way. So that runs through the slabs. The slabs were the things that we added to the wood floors to add mass to the house. In the context of this talk, however, air quality and material use is kind of primary. And so the two aspects that are the most critical to air quality of a project like this are how you ventilate and what materials you choose and where you put them. And so that's primarily, I think, the way that I can address this issue here. The ventilation systems in the house, there's really two primary ones, as I mentioned before, but there's the typical window system. So we used an unbelievably energy efficient window that comes from Germany, and we had to couple it with the Danish company that we work with in order to make sure that we could fit all the systems into the window. But what happens is the top light of the window is the automated light and the bottom one is manual. And so you can, of course, throw off the balance of the house if you're using the manual windows incorrectly. But there are essentially alarms that go off when that happens that allow people to understand how to use them better. And also the manual windows can try to adjust for any user error. And then there's the solar vent in the back, which actually is more there to drive the higher occupancy spaces in the basement of the house. How we tested this, how we proved it out is one of the ways that these kinds of projects differ from our normal projects. We do a lot of simulations in the concept phase, a lot of CFD modeling. The beauty of this project was that we were working with an initiative, a group of PhDs that do this all the time. So they were essentially part of our design team in this early phase. So these simulations, external CFDs, internal CFDs, to make sure that window placement, where the manual windows go, how far they can open, how much you can disrupt the internal temperature in different parts of the season, how that air gets distributed around the house or in a single room, all of that was proved out in the concept phase. And so And then what we were able to do from that, after we could quantify that a little bit, is to start to put some best practice into place. And so one of the things that we discussed before we came to this talk was how I could, in a very short amount of time, frame a discussion that maybe can make a difference to people's practices. So I think of a couple of ways that I could do that. And they really center around, on your material use and your ventilation practices. How can we find some shortcuts to make sure that we can, everyone can do some of these things and do them well? In this house, what we followed was the red line principle, which might throw you off a little bit because there's nothing red on that slide. But it's a principle that you have a boundary that you don't break. And so, in Norwegian practice, they use that term a lot, the red line principle, where you basically draw that red line around your plans, around your sections, around your details, and make sure that that is unbreachable. And that red line can mean different things. So in this case, I've drawn a blue line, which indicates where the vapor barrier is in the section and in the detail. And then there's also, of course, a weather barrier. But they are doing in some constructions, they are the same, and some they are different. And so this is a little bit more of a rain screen type cavity in the wood in wood construction. It's more of a Norwegian way to build. But what it does is the blue line is critical. So that is where anything inside of that line, any material inside of that line, you have to be hyper in control of in terms of the interior air quality. Anything outside of that line, you want to be careful of as well in terms of a holistic project, but it's not going to affect the indoor air quality nearly as much. The other interesting way to approach shortcuts is to think about some of the certifications, of course, that we all know about. Some of these you may know about, some of these you may not use day to day, but these kinds of shortcuts were really helpful to us because we had to do a deep dive in terms of materials. Every project you do a certain amount of that, but on these projects you have to go quite a bit deeper, not just in the detailing and design phase, but also in the construction phase, because as the designers and architects in the room probably know, the moment you get into construction, everything goes out the window, and contractors start asking you to switch out everything that you started with. And so you have to figure out a way to respond on your toes to kind of keep the goals in mind. So all the way on the left, you have some of the most basic things, finding materials that are NAF or NAUF, no added urea formaldehyde. VOCs and TVOCs, make sure you have 0 VOCs. I mean, these are kind of things that we can all do. But then other certifications, the CARB 2 certifications for California Air Resources Board, another kind of key thing to look for in material properties that you're working with. The Living Building Challenge Red List for furnitures, materials in your furnitures that are on the red list. That chemical list can be extremely helpful. The Healthy Hospitals compliant materials, that's another really good kind of rule of thumb that you can apply. You look at your materials, especially your furniture, you look at your furniture list and try to make sure that you use those kind of HHI compliant materials in your furniture. And M1 emissions compliant, more of a European standard, but you can find materials in the US that are like that. So again, the key things that you have to focus on are the materials on your left, wood, stone, et cetera. The more natural the material, the less finishing that it requires, the better you're going to be. Your insulations, if you can avoid any kind of petroleum-based insulations, which are most of them, but there are options, right? There are wood fiber-based insulations that have to be built in a specific way to work, but they can replace them in most cases. Denim-based, recycled insulations, things like that. Those can start to replace all of those, high carbon and also harmful chemical environments inside your buildings. Another big one, paints, sealants, glues, that's huge. And so what often happens is you have a great spec, but then you get in the field and some contractors don't read the spec or read the whole spec, and they come in with their glue guns, they come in with their caulk guns. All of these things are problematic. So you have to be really in control of everything that's going on in the site. And then going all the way to the right, the furniture is critical. The furniture, you can do everything right and get your furniture wrong and have a pretty bad indoor air quality environment. And so I'll just kind of take you on a quick tour of the house. This from the outside of the house. We reshingled everything in kind of natural cedar, no finishes. You can see the windows I discussed. On different sides of the house, they have these hoods around the windows that respond to the different angles of sun, so that they can basically work as sun shields in the summer and allow light in during the winter. the inside of the house. We removed as many partitions as we could to make sure that we can get light transmission all the way through, but also, we always had to follow the basic natural ventilation principle that every room had to have at least 2 sides with an opening in it. So that also, required us to remove as many barriers as we could. This is the first floor as you walk in. So you can see down to the basement where they have group spaces, and then, of course, the working spaces are above, and this is a main administrative floor. Again, these offices, when you just walk in, they're pretty stripped down. We use the shelving on the right as actually a light bounce to get light deeper into the space. Pretty minimal. The furniture, we worked with this. I think these were, if I remember correctly, these were Steelcase. So we worked with Steelcase to customize their furniture, but we had to make sure that the things that we started with were HHI compliant. Some of the materials were custom. So we worked with the GSD students to fabricate some of the things, like in the stairwell, all of these kind of custom shaped panels, which are acoustic based. But again, going back to the basic material principles, we have to make sure that the plywoods don't have urea formaldehydes in it. We have to make sure that the insulation behind it that works as an acoustic buffer throughout the house, that's something that basically doesn't have any emitting materials inside of it. The working spaces on the floor above, so you can actually see this is level 2, and then you can see up to level 3 above, where we stripped away most of the attic so that you can get light from the skylights down to the workspaces below, and you can have more kind of visibility between there's a couple little lab spaces at the top that you can see there, and the PhD desks and working environment below. Small spaces, large spaces. There's a little phone booth that was a kind of a part of the stairwell that got actually captured into the floor plan of the working spaces. So we used a kind of minimal number of spaces and walls and materials over and over again to try to achieve maximum benefit. And then, as I mentioned, the kind of larger group spaces below. This is the new larger meeting room below. In the future, if we can proceed into phase 2, there will be an even bigger meeting space in the rear yard as we expand the house. But you can see, even in the basement, where we're almost 4 feet below grade here, plenty of natural light. We use things like, there's actually natural clay materials on the walls here, that not the writing surface walls, but all the other walls, so they actually help absorb and release moisture in the air, but they're also absorbent of some of the chemicals that so the remaining chemicals that are in the house. So with that, I think I'll say thank you.
Good morning, everyone. It's certainly an honor to be up here today, especially after after Laura and Aaron. So thank you for the invitation to have me here today. So my name is Ginger Creek Dozier. I'm a CEO and co-founder of Biomason. My background is in architecture. I went to Auburn University, fell in love with materials back when we really didn't talk about materials or what materials were made of. All we knew is that this was our, canvas as architects and designers to choose materials and make amazing things out of them. What I want to talk to you today about is a little bit of a journey, but also a little bit of more of some education about a product that we've been developing at the company Biomason. And, from an architectural perspective, when we really start looking at how materials are made, most of them are mined, heated, fired, at extreme temperatures. The construction industry is quite innovative avertant. So there's not a lot of development that's happened, since really, in my opinion, glass, and then now a lot of amazing things with wood, but it's a pretty conservative type of industry. But really, when you start digging into, how some of these basic materials are made, such as bricks, and you see this image, of firing bricks, not only is it, emitting a lot of, CO2 up into the air, but there's a lot of particulate matter. The bricks are hot. There's a lot of human endangerment that happens within that. But what I want to focus on today is more about concrete. So concrete is the second largest consumed substance on Earth following water, which is staggering. And because of that, the production of Portland cement is responsible for over 8% of global CO2 emissions. A lot of this is because of how Portland cement is made. If you don't know how it's made, there's a really fundamental analysis. They mine calcium carbonate and they burn the calcium carbonate just to get the calcium. So the carbon goes away. So for every ton of Portland cement that's produced, a ton of CO2 goes up into the air. So nature has a little bit of a different way of doing that. So this is a lovely image of coral, and you can see the skeletal matrix inside of that. What's unique about coral is that some species of coral have this structure that's actually stronger than concrete. It's grown in a natural environment. It doesn't harm the surrounding environment. It extracts what it needs from the ocean environment. And so that's been in my mind for a long time. In fact, this is a little image of 7-year-old me at the beach, the first time I went to the beach. And you can see I had nothing to do with the water. I just wanted to dig and find stuff. So I have quite an extensive collection of shells and rocks from probably before I was 7. And I've toted them around everywhere, and they're heavy. But it's... I've always been fascinated with them. And what really fascinated me was, how are they made? Like, it's just this beautiful, structure, but also when you start digging into, the fabric of the material, it's, you're starting to look at layers, and you can start to see different deposits that are happening. And I was just blown away by that and really wanted to know, how was this made? So I had an idea one day where I wanted to grow a brick. I had just finished reading the book Biomimicry and was highly inspired by scientists that were developing glues that mimicked barnacles and muscles and gecko feet. And I really started to think, well, okay, all right, if nature can grow these coral reefs and seashells, why can't we grow construction materials in a very similar way? So that's what started this journey, and I won't go all into the depths of it, but I will say that I converted more than 2 bedrooms into labs. I didn't have guests come visit for a while. I met my husband during that time. He still married me. He's still with me, so I didn't run him off. But honestly, it was a process of iteration and trial and error. It really went back to a fundamental aspect of how are coral reefs formed. What I learned is that there's a symbiotic relationship with a microorganism, a bacterium, that forces a change in pH at a local environment, which was fascinating to me. So it's almost like 3D printing, like templating the different organisms that's really making a pH shift. So that's what started that. I made thousands of bad bricks. They were awful. Some of them were crumbly. Some of them would never dry. But over and over and over until I figured out how to make this work. So the fundamental recipe, if you will, for this is we start with aggregate. It's 85% of the final product. So really what we're doing is very similar to what you would think of concrete. You take an aggregate and you fill it with some type of adhesive. So we use 85% aggregate. It can be natural aggregates, waste aggregates, high performance aggregates. I started off a lot of research when I was living in the Middle East, which is a lot of fine sand. It's very difficult to work with. It's alluvial, meaning that it's rounded in shape, which is great to work with. However, because it was so fine, it was honestly like trying to learn how to play basketball with a tennis ball. But that taught me a lot of early lessons. Because I actually switched into, well, let's think of some waste aggregates. Instead of trying to use all these natural sands around the world, which we all know is a bad idea, trying to find aggregates that are waste and utilize those into a construction material. So I learned in different mining entities that you have a lot of fines. Even in construction demolition, you have a lot of fine aggregate materials that it's very difficult to make anything with because ASTM has standards for the size fractions that you can use for concrete versus asphalt. And what we use is actually something well below those sizes. We use something that's called wash screenings or fines. They're really beautiful. So what we do is we take those aggregates and we mix them with our biologics, which, what's great about starting companies, you can name stuff. So we named it BioSpark and BioNutrix. So BioSpark is the organism which, activates the process, and the nutrient is actually what gives the metabolism to the organism so that they can continue to produce that pH shift. With that, we add a solution, which we use water as a carrier. It's a nice highway for us to deliver the nutrients and calcium source to the organism. And then between 48 and 72 hours, and it depends on what strength you're after, you have a final product. And, it's interesting because the scale of this, the production honestly looks like hydroponics, but mixed with traditional equipment that you would find at a typical concrete block plant. So one thing that we knew early on was we didn't want to invent something where everyone had to wear a lab coat, to be able to make this product. We wanted something that, really could slip into existing manufacturing. So when you look at under SEM, so scanning electron microscopy, what's happening is you're building a structural scaffold around aggregate particles. So unlike concrete is one shot. You essentially mix all the materials up, and you don't necessarily have all of your aggregate particles sphere packed or linked together. So what we're doing is we're building a structural cement in between and around aggregate particles. And it grows almost like rings. So you can see the growth happening. Where the organism is creating a biofilm around each grain of aggregate, and then it continues to grow outward. So in our production system, we don't start off with bricks that are this big and then they grow. We're essentially making the product more dense, if that makes sense, within the process itself. Some attributes about it. So we, one of the first board meetings that we ever had is we decided, to list out cost, quality, scale, and life cycle analysis as our guiding principles. Because honestly, every decision that gets made, happens to be around this. We didn't want to create a product that was prohibitively expensive to be used in construction. Quality, it better be stronger than concrete. Scale, we need to be able to scale this, and then life cycle analysis, in my opinion, it's not that it's taken for granted, it's really how the company really started off, but it's, again, another guiding principle. So I won't go and read all of these, to you, but, essentially cost, it's low cost in direct material and labor. We have the components that are activated by water, which I geek out on because it's really exciting when you have, the organisms that are essentially dormant and their shelf life is approximately 500 years, and then you can activate them when needed. It really helps just in terms of thinking of supply chain in the future. Quality, we're stronger than concrete, which is amazing. We can actually program the strength. A lot of this is a function of time, but it's also a function of inputs and changes in environment. So that's made it exciting for us because it started to unlock or get us outside of the box a little bit and thinking about other applications. Scale, they don't shrink during manufacturing, so what we press out is actually the size that it grows to. And I already mentioned we use existing equipment and it's an automated process. But I think on the life cycle analysis part, what's really important to note is that all this is done at ambient temperatures. So we're not using heat, we're using human comfort as our temperatures within that. Non-potable water can be used. There's actually, in some cases, advantages of using non-potable water with biological systems because there are a lot of goodies that are still in the non-potable water for the organisms. Here's something exciting. We learned that it exhibits self-healing properties. That was a crazy day. We had a unit that was growing in the process, and we pulled it out, and we accidentally dropped it, and it wasn't ready yet, so, it basically just kind of cracked in half. So we're like, yeah, let's put it back in. And it grew back together. It was very exciting. So we've actually taken that and, looked at other different applications, which I'll talk about in a little bit, but some are really fascinating, of cements that grow underwater that never die. They self-heal, and they just use what they're extracting in the natural environment. All right. So right now what we're doing is we're building plants. That's very exciting. I love scale. I want this to be, in every country around the world. So what, this is an image of is really part of our production process itself. Again, it's very similar to how concrete masonry is already made today. We grow it in a vertical system. Right now we have a product that we call BioLith. I have a small sample board outside here, and then I have one in my bag called my purse brick, if you want to come look at it. We decided to, we started with, facing brick sizes. We've actually moved to thinner masonry, longer masonry as well. It doesn't mean we can't do larger pieces. It just turned out like the market that we were really targeting in our early years chose a thinner product to be used. So I have some images of just some of the recent installations. The product, it's rated for interior and exterior use. It's also rated to be used as vertical surfaces or horizontal surfaces. We wanted the PSI to be more than 4 times the strength of a concrete block. That was a big goal that we succeeded on a couple of years ago. We now have some products that are actually 3 times stronger than that. Here's just some different examples of some of the installations. We're starting to get into more of the demonstration phase as we work together with our partners. There are a lot of things that you can do with a material. What's crazy to me is that we waited 5 years before we polished it with a polisher. I don't know. I guess I'm like, no one polishes bricks. Why would we do that? And then we realized, wow, actually, the product itself is a natural stone. I mean, all we're doing is growing natural stone, sandstone. So it's, sand and calcium carbonate or aggregate and calcium carbonate around it. So we have different finishes that we can do. We can also add different materials on top, broadcast, so looking at different aesthetics, but also even adding different performance additives to that as well. We actually started, one of our first projects was in San Francisco at Dropbox's headquarters for an order of pavers. And it's a funny story because this was years ago. This has actually been installed for about 4 years now, and it looks great. But when it was just 3 of us in the lab, we got a phone call from William McDonough Partners, one of their firm leads, and they said, we'd like to place an order. And I said, can you tell us a little bit about the project and the timeline and the quantity? So throughout the conversation, it turned out that it was, they wanted the entire building, which we're like, we love to do that, but, we're just getting started out. So I talked them into 2 small courtyards, and that was really important, for us to just jump into scale. There's nothing like having to figure out scale when you have an order that's due in 3 months. It was great. So one of the things that's important to us is transparency. I'm trained as an architect. I understand the importance and the need for transparency and education in terms of what that means. We do a lot of data. We collect data like NASA around ourselves. But one of the things that we really like to do is look at how we compare with different materials, and then, as different versions of the technology, we're actually going to absorb CO2 as part of that. So I'm excited about that. But right now, we're not emitting anything. Again, it's like a natural stone, so we're not using, heat or energy processes for doing the biological process itself. So this is just a snapshot when you look at how to compare the different levels of CO2 that happens from different materials. There are governing things. There's mention before of different certifications. There's so many of them. For us, we're honestly, a lot of times, going through a lot of different cycles of what's important to, for us to be able to communicate, since we're quite open about what it is that we do. We have nothing to hide. So we are certified through Cradle to Cradle. There's a lot of different aspects of Declare and LEED and EPDs. So we're, constantly doing work on that to keep those different groups up to date. But one thing I love about Declare is that the way they frame it's the building nutrition label for construction materials. Like that, what a great way to think of, really being able to analyze a construction material is really thinking about it the same way that we analyze food labels. There's a lot of teeny tiny text here. But, essentially, if we're just looking at LEED, there are some aspects, that really help us with LEED. And something that I really didn't talk too much about, but we use recycled aggregates. We use aggregates that are considered waste. So there are different points that are associated, with that. You can use the product to, in existing buildings. It's not that, you have to have a different way of installing it. It actually uses the same installation methods and the same, materials for doing that. Although we will invent mortar next, I promise. So, other things, packaging, that was fun. We got to figure out packaging. How we wanted, these pallets of materials to be delivered to site. So we are completely plastic-free at BioMason everywhere. And it's important to us, to really understand, the aspect of waste. So we like to use materials that dissolve, and they go, they're nutrition for the soil. Other things are, I mentioned before about the finishing aspect. So we're not using a chemical or wax or anything to cover the product itself to make the sheen on it. We actually just polish it like you would a granite countertop. And then indoor air quality, there aren't any VOCs. I mean, it's just limestone, essentially. And that's, again, very important for us in being able to communicate that. This is the team about 4 months ago. We just hired more. We're up to 34 people, which is very exciting. It's over 150 collective years of manufacturing expertise, but also 18 different disciplines, which is very exciting. And it takes a lot of people in different backgrounds to really be able to work together on this. One of our principles is that we're doers. So we don't just talk about what it is that we do, we actually do and experiment and go through. And as I'm looking at this group, one of the things that I've highlighted most today is our product Biolith, which is our tile, it's our masonry product, but we do so many other things too that, again, it's the power of biology, looking at using a process like this to do dust control. We've worked with the Air Force on some runway development. We do work with the Department of Defense on an underwater cement, which I mentioned a little bit early on too. So, I hope that I would like to leave you all inspired that, just because you're trained in architecture doesn't mean that, you can't learn and build all of these different things. And I think that we need a lot more thinking about, organisms. Personally, I love them. We only know 1/1000th of a percent of all the microorganisms on the world. And, as mentioned earlier in the kickoff, Maya, we're losing them. So anyway, I hope to leave you inspired today. Thank you.
I don't know, does this work? Yeah. Wow, that was totally inspiring, all three of you. And Maya, I feel like we're up to a large charge. You set the bar high. We're trying to change. So we have just a few minutes for a discussion, but I think that we heard we are not fine. There's a lot of chemicals in amniotic fluid. There's a way to redline for IAQ that microorganisms are needed to form coral. And it just strikes me that there's a lot of different languages that are spoken in these different disciplines, and yet in order for this change to happen that Maya charged us to make, the interdisciplinary discussion is really necessary. So I just wonder if you, each of you work with other disciplines outside of your own and have to speak languages outside of your own language of your field of expertise. And I wonder if you would talk a little bit about describe that as how it kind of informs your practice, maybe challenges your practice, both?
Well, for me, I think there's a bad attitude in a lot of science that if I can explain it to my mom, then she won't think that I'm smart, right? So I better use the big words so that she'll know how smart I am. we have to reject that. And we need to train whoever comes behind us to not only speak to our colleagues with that jargon, learn to speak the language of whatever discipline you're in, but also to remain grounded in the language of humanity. And I think we all have to become, I call it scientific storytelling, maybe you would call it something different in your discipline. We have to become better at telling the story of what we do, because I don't care whether or not you think that I'm smart. I want you to care about what I'm telling you, right? If you care about what I'm telling you, then you're going to do something about it. And you're going to do something about it in your discipline, whether that's chemistry or engineering or math or art and storytelling. So we have to re-embrace the value of communication.
I would say on my end, I mean, the value of being an architect, maybe the coolest thing that I find to be kind of re-engaging me every time in every project is the power of being a generalist. What we do is, our clients are our collaborators, and they're all different, and they all, not only do they have different businesses that they run, do they have different ways of doing those things, even when you're working within one sector. We have to kind of inhabit them somehow each time. And so, I often find that, all of my learning happens whenever I get to inhabit some new client, some new type of, doing whatever it is that I may have thought that I knew how to do before. And so to me, anybody who's, going to architecture school, who is a practicing architect, I would imagine that one of the inspiring things that you would encounter every day is that you may not get to dive as deep as you want in any one subject, which I'm super fascinated by everything that we've seen today. I mean, from the kind of chemical side to the manufacturing side. I mean, I would love to know more about all of those things, but in order to know more about more things, I have to kind of decide how deep I can dive. But I really think it's, being open to not pigeonholing yourself into one type of project, even if that project is doing amazing things for the world, which, that's a congratulations in and of itself. I think you have to find a way to adapt it over and over again to different industries, different clients, different people. That's really the value of what architects do. So,
both amazing comments. I don't know if I have too much more to add, except the aspect of just making sure that communication is understood. So I think you referenced that earlier about, not necessarily using the big words, but I think for me, what I learned was my strength was just being more of the connector between the disciplines too. I didn't understand everything that everyone was saying, but also, looked at how can we get all of these people together in the room. And it's almost, maybe it's some of the background in education, like of the design thinking aspect probably, but I felt it was more important to, let's get all of these disciplines together and talking so that they can all understand one another. Maybe there's some bizarre moments where you have to translate in between that, if possible, on that.
Yeah, I mean, I think that the thing that just strikes me after seeing all of your presentations is that this intersection of design thinking, architecture, and science is essential. And yet, a lot of people say, like, architects and designers shouldn't have to learn chemistry or shouldn't have to learn science, or, we have too much in our curriculum already. We can't also learn this other thing. But at the same time, it feels essential in, if we're charged to make this radical change. And so I just wonder, like, what you think about that, or even Laura, like, do you work with designers and architects, or how would you think about integrating that in an education of a designer or an architect, science?
I often will say, you shouldn't have to be a chemist to go to the grocery store, right? Like, we're asking a lot of just the average consumer, let alone people who are working in a professional environment, to try to think about these things. to me, again, I think it comes back to partnering with the right people. I can't do what these folks do. I mean, did you watch me while I was watching that? My mouth was open, I think, the whole time. And it's awesome to be surrounded by people who are brilliant in their own field and do something totally different than you. We don't do that enough. We spend time in our silos, or as one of my mentors would say, we spend time in our cylinders of excellence. And we don't even realize what we're missing out on. So no, I don't spend much time talking to designers. I answer the phone when someone calls me, when people reach out, but I think in each of our own worlds, we're not being proactive enough about saying, hey, come tell me what you know. And then I can think about what I can do with that information. And you tell me what you know, because I learned so much here that I want to teach my students now.
Well, I mean, coming here was an invitation to talk, but the reason I actually usually show up is to listen and to hear in these kind of formats, all of these people coming from different backgrounds and that are doing the most fantastic things, some of which I'd never even contemplated. So I think that the network that you build, and even you all in this room, seeing and hearing these things and probably coming up and talking to people afterwards, is critical, and networks are really important. I mean, I imagine I almost always follow up somehow with people later, because when there's the right moment on a project, that's when I try to make something happen and reach out. And so we sometimes on some projects, especially some of the projects that I showed today, we work with a building scientist. So not maybe a traditional scientist, but a building scientist in Norway who's a partner on almost all of these projects with us. And his networks are different than my networks. And he reaches out to people that are more pure scientists and says, you should be talking to this person, you should be looking at this material. And so in addition to actively working with us on these projects to analyze from a scientific perspective how the buildings are going to perform, how the energy is going to flow in and out of a building, he's also connecting us to people that are deeper into these fields. And so that to me is the only way to, you have to build your networks, you have to talk to people who have strong networks and kind of keep going through those channels.
Yeah, that's great.
I heard this story a while back when William McDonough was teaching at UVA, that he had a seminar and all the students showed up and, he had a pizza, so they all ate pizza. And towards the end of the class, one of the students said, hey, where's the syllabus? And he's like, oh, yeah, your job is to find out where every single ingredient came from in that pizza you just ate. And I don't know how many years ago this was, but I thought what a great way to educate the architecture students in this case, but any student really, to figure, they had to dive through all the chemistry aspects, where, supply chain, transportation, and, by the end, can you imagine how fascinating the whole room was filled with, probably some bizarre story about how this one can went to 8 countries before it ended up, in the country where the can was consumed. And I think that type of way of thinking or educating is so mind-opening, for students, and I wish that I had taken the pizza class.
Sounds like you're doing it. I wish we could talk a lot longer. I hope we can continue this conversation over lunch and over coffee breaks and later over a glass of wine. And I know that there's many people here who want to speak with you as well. We're on to another amazing panel. So thank you so much.
Thank you.
Thank you.